Hello everyone, it's October 10th. Alright, so today's goal is I finished the target, this thing, and after this, we're gonna go back to my calendar and then go through all the solutions, and we'll see how they work. Okay. Alright, so this one, increasing triplet subsequence. Given an integer array nums, return true if there exists a triple of indices such that ijk in the sequence and the value is like this. If no such indices exist, return false. Any triplet has false. It's true. Can you implement a solution that runs in O(n) time and O(1) space? Okay. O(n) time, I was thinking about sorting, so sorting is out. Cannot do O(n) time in sorting. We just want 3, a triplet, such that they're in the order and also the value is also in the order. Huh. The hunch is what's that called? Monotonic array. So let's say monotonically increasing, right? Not increasing if it's bigger, if it's smaller, will pop into. So smaller pop, bigger. So 2, 1 will pop 5, and 0 will pop, and 4, 6, 0, 4, 6. We got 0, 4, 6. I mean, 1, 4, 6 is also working, but so anytime when the monotonic array has a length of 3, then it shall work. Let's try it. Did I not? No, I don't think so. Not 100% sure about monotonic array, but I think that is just any time that the length is 3. Because if it exists, right? If it exists, then no monotonic array, it definitely works. All right, for any nums, right? If len stack is equal to 3, return true. So I want 3, right? Otherwise, while stack and n is larger than stack minus 1, stack.pop, stack.append n. Actually, we'll do it here. Return false. False. Increasing. The heck? Did I do the opposite one? Yeah, I think you did the opposite one. Should be smaller, right? Then smaller equal to. Yeah. All right, let's try. I can produce some test case for this. Okay, let's do 10 test cases. Let's do minus 100 to 100. Let's do 100. Oh, and most likely it's going to be true. Yeah, most. You know what? That's not the right way to do. I think the right way to do, well, first of all, this is the edge case. Oh, that has to be, yeah, do 1, right? 1, 2, 1, 2, 3. These are the edge cases. And then we do, let's say, 5, 4, 3, 2, 1, right? 0. But then we rotate, let's say this one become minus 1. Right? And yeah, let's get minus 1, 1, minus 1, 2. Should be good. Because usually if you do random number, I'm pretty sure it will all be true. I mean, if you don't believe me, in fact, let's just do 10. I'm sure all of them are true. Because random, it's very likely has 3 increasing. I think all of them are true. Yeah, it's very hard to get it not true. Oh, I've done this before. Ugh. Oh, dang it. What's the answer? Expected true. Huh, interesting. 10, 12, 15. 10, 12, 13. Shoot. Interesting. Ooh. What do you make of this? 10 will pop. 10, 12, 5 come in and pop all of these. And then 13 comes in. 13 comes in. Yep, that's not right. I mean, we can set a rule. Let's say, yeah, but that's not, like, let's say we have, Okay, if any time is 3, right? And then it could be like at the very front. And something extremely small sweep out everything. Like all the build up is gone, right? If all the build up is gone and I just don't have enough. If I do have enough to keep piling up, then maybe, right? And maybe. What should I make of this? Don't go all the way to the end. Let me think. All right, so as we go, right, we go. It's guaranteed that at the current, the first one is the smallest. It's guaranteed, right? It's guaranteed whenever I come in, what we have is the smallest and the second smallest so far, right? This is guaranteed. So when I come in and if I am smaller than the smallest, are you saying I should not append myself to it if I am smaller? Well, if I'm smaller than everything, then we need to build up again, right? Just think about the situation. When you have something that's smaller, if you just replace one, then there's no loss, right? Yeah, it's fine. If you replace one, there's no loss. And yeah, if you replace one, there's no loss. But if you replace two, which means you will go to the first one, then we basically we lose one, right? We lose one. And for the remainder, we need to compensate. So if I have something that's bigger than me, but smaller than that, then this one can come in. It basically means if I have enough left, then it is desirable, right? If I have something extremely small, but I have enough left, then it's desirable to replace everything with the smallest one. Because if there's something bigger that can make the original work, it will make the current work. And if it's something smaller than the original, it can actually make the current work. So no matter what, it's a good choice if I have enough. But if I don't have enough, like in this case, if I replace, I only have one, right? I only have one left. So if I have only one left, then it's impossible, right? I just cannot. So at least I need to have two left, right? Which means if I am going to replace everything, then I need to have two, at least two left. Otherwise, I shall just not consider, right? Because if I consider myself, it's not going to work, right? If I consider myself, it's not going. I'm just going to kick out everything. And it only applies to if I'm smaller than the smallest. If I am bigger than the smallest, then it's fine. You can just replace it. Doesn't matter, right? Doesn't matter. Yeah. Okay, let's see. Let's see if this is the thing. So what we're saying is, if n is smaller than stack 0, and, oh, we need I, in this case. The number left, so it's a len nums minus I minus 1, right? The number left, so if I replace, I need the number left to be larger or equal to 2. So which means if it's smaller than 2, right? If it's smaller than 2, the remaining is smaller than 2, then continue. Wait, index out of range. Huh? I would just say stock. Yeah. Not sure. I want to try it. maybe that's the edge case. So what I think is, this is the edge case where we have a small value, a very small value, right before the end of nums. We say, since this small value would knock out everything in nums, we shall only do so if there are enough values in nums, right? Enough values in nums to support at least another round of triplet. If there are not enough values left in nums, we should ignore the small value, current very small value, because yeah, it won't benefit us. Okay, I don't know, let's try. What do you think? I don't think it's gonna make any difference in this one, but I'd rather just try it out. Okay, let's try this out. See how it goes. Oh, I think I hit it fundamentally wrong. Man. This is bad. 2 days in a row, I wasn't able to get it right in the first shot. Come on, man. What the hell? What the hell? What's this one? 1, 2, 3. Oh. Okay, that's more like a typo. Ha! Now we do try and error. Damn. Alright, I think there is something fundamentally wrong with this. Something fundamentally wrong. Alright. 9, 10, 5, 11, 10, 9, 8. We have is that true? Nine, 10, 5, 11, 10, 9, 8. 9, 10, 11, I see it. Oh, it's not just happening at the end. God. I see, 9, 10, 11. Oof. How do I reduce this? thought I can resolve this, but no, I cannot. What do you mean by wrap around? Put 19 at the end? I don't think that will work. Maybe we need to keep recording. Like every time, because if you swap 1, that's no change. But if you do 2, then you're reducing. So let's say every time when you get rid of everything, you need to record the largest value so far, right? You need to record the largest value so far. So when you move on, you compare current one, right, to previous one, and then say if it's bigger, then you allow it. So we have that kind of 2 things going on, right? So we have the previous middle value, and we try every time we try to get the smallest previous middle value. So here's my idea, my new idea. Yeah, this is not working. This ain't not working. So we'll do this, right? And we can say previous mid value. I want the smallest, so let's get the largest one here. And I don't think I need this. This method doesn't need enumerate. So we'll just do this, doesn't matter. And then we say if not stack, which means I popped everything. Huh. Ah. Oh man. Every time we say if a len stack yeah, equals to 3 is true. And if len stack is equal to 2, then pre-mid equals minimum pre-mid and stack this, right? I just want a mid value. And then this one comes in, swap out, I say if not stack, right? Actually no. We get the, hold on, I have a pre-mid, right? And then we do this. And then we always check. We say if n, and then pre-mid is only available. So if n is larger than pre-mid, then we can return true as well. If not, we'll do this. And then you can pop everything, it's fine. Because I already got the pre-mid if I have to, right? And then we do this. This is not going to be coming back. This is not going to be. This is whatever the previous is. So if we do this, this one will pass. And everything will pass. So we have a pre-mid here. Okay, can we do this, say a little bit nicer? So many if statements. Okay, let me try this one first. I have this pre-mid thing. Oh, it's gonna pass. This is not really as good a test case. Oh, I don't remember doing all this, or maybe it is. I don't know. Must be a lot of method I tried in the past. Yeah, it's harder than I had expected. Actually, much harder than I had expected. I thought monotonic array, done. But yeah, I thought this problem was easy. Monotonic array, and we're done. However, there is an evil twist. Such as the test case, this test case specifically. Right, such as the test case. So just doing monotonic array would miss the test case above, because when 5 knocks out everything, in the array, we are losing candidates. Generally speaking, if the current n replaces only one value in the monotonic array, it's fine. We are not losing or gaining anything. We're not losing anything, and in fact, we are gaining, because we use a smaller middle value to replace a previous middle value. However, if the current n replaces both values in the monotonic array, we are losing 2. We have a net loss of 1 value. This could be deadly. Therefore, the solution is to always to keep track, right? Keep track of the smallest middle value in the past when the monotonic array hits length of 2, right? And for each new n, we first check if n can be paired, right, with, if n is bigger than the previous smallest middle value, right? If it is, then we have an answer already. Otherwise, we do the monotonic array business. Yeah. What was the solution in the past? 61 test cases, 76 test cases. Yo. Binary search. Okay, I'm curious. I'm going to look at all my solutions in the past. Binary search. That is not expected. I was all for monotonic stack. Oh, keep track of the smallest two numbers. Man, this is the monotonic stack, but we make it very explicit. Oh, wow. Alright, this is my solution. Monotonic stack. This doesn't need monotonic stack. Binary search. I don't think it's necessary, but yeah, this is pretty dumb. A monotonic stack is pretty dumb. And we're doing exactly, you should know that the monotonic stack doesn't go larger than 2. Right? Holy crap, this is so dumb. Monotonic stack is so dumb. We only need to keep track of the 2 smallest value so far. No need to use monotonic stack. We can still call it a stack. Yeah. And then for any nums, right? Say if n is smaller than stack 0, stack 0 equals. Oh, hold on. I need to wait. Hold on. This is monotonic stack. This is another implementation of monotonic stack. Right? If the current value is larger than this, then we're done. If the current value is smaller than this, then we swap it. But we don't delete this one. So what we're just saying that we have a current value that is smaller than this. So we just keep the smallest, right? And if a sum value is larger than this, then we swap in. So this is, okay, hold on. This is essentially, okay, this is essentially still monotonic stack. But the big difference, right, is that we don't pop everything if the current value is smaller than stack 0. We can do this because we know if it was 2 values, the sum value must be here, right? So something in the past is small, but we're trying to update, try to make it as small as possible. This is important, and this allows with no popping, but only replacing. We make sure that any build up, right? Any build up of the stack previously won't see loss just because we have updated the smaller value. So yeah, if this, then we just say n, right? If n is smaller than stack 1, then we update stack 1. Else, then we return true. Then return false. Yeah, this is the one. I think it's smaller or equal to. If it's smaller, hey, hold on. If it's smaller, yes, now we do 1. The next one, it should be equal to. Should be smaller or equal to. Because otherwise, equal, we come out, it'll be wrong. Was it smaller or equal to last time I do it? Don't remember. It is smaller or equal to. Damn. It's smaller or equal to. Alright. Yeah, it's pretty bad, huh? Alright, calendar. Okay, I remember what it is. Let's see. Yes. Intuitive analysis is the most intuitive to me, but of course this is not right. This is what I come up with, which is kind of, I don't think I can come up with this again. Let's see, this is a sweep line. How many events are going on at this time point? And find a time point of the max number of events. Every time we book a new event, what we actually do is add 1 to the event counts to all time points in the range. The final result of each book call is exactly the max count of a single time in the whole range. This is a segment tree. We add 1 to the event count to all. I was thinking about segment tree, but segment tree handles a single point. A single point. You're telling me the starting point. If the starting point is within, then we just add to all of them. You know what? I don't need to record this. I'm gonna just read through this, but I'm gonna end it today. Yeah, I need to go through all 3 approaches, especially the segment tree. And I'll probably also practice again the segment tree and update. Yep, I think I see it. Self-doubt vowels 1. Self-doubt vowels 1. That's interesting. Alright, I will see you guys tomorrow. Yeah, I'll just keep digging into this. Adios.